Welcome back to part 2 of Time in Geology. I'm not exactly sure the title of your book uses, but that's what I'm giving it. Let me reset my clock. Okay. Excuse me. I had a piece of apple. I was just eating in between the break there. Here's our key. We've got sandstone, which is this. Now, you know that sandstone forms either in sand dunes on the land near rivers or in delta type areas where you have fairly fast moving water. We have conglomerate, which forms in valleys on land or in fast moving rivers. We've got shell, which forms from mud. We've got limestone, which forms in shallow seas. We've got granite, which forms from molten material. So what's the history here? Sometimes it's easiest to start with the top. So we know that the last thing that happened was sandstone was laid down. It could have been sand dunes, although it doesn't show cross-bedding, but whatever, we have sand here. Here we have conglomerate, which means this was on land. The rocks were rounded, so they were probably in a riverbed or something like that. And you can see this if you go to, about 16th Street and Union Hills right near North Canyon High School. When you pass through that little hill, you'll see that either side of Union Hills has rocks like this. It's really loose material that's trying to turn into conglomerate rock. That was an old valley at one time, and now it's a hill, which is kind of unusual. So sandstone, then conglomerate, and then it was in a lake or a sea because you have shell, which is mud, being stacked up. Now, before that, you've got this wiggly line. What happened to the rocks that were here first? They were shaved off by erosion. So in between this point right here and this point right here, could be hundreds of thousands, millions, maybe even a billion years. You've got a lot of time missing. We don't know. But this is relative time. We're just putting things in order. What happened before the shale? What was first? The limestone? Or the granite? Well, if the granite came through the limestone and intruded into it, the limestone had to be there first. So I think the thing that happened previous to the shale was this. It came through and then it got eroded off too. What came before this? Well, this cut through that too, so it looks like next was the limestone, and then here's an erosional surface too, and then the sandstone. So let's go in order. Up. From oldest to youngest. The sandstone was laid down, then the limestone, and then the granite came through, intruded its way in there, and if we had a really good drawing, you'd see that this was baked right along the edge through contact metamorphism. And then something eroded this, so it was pushed out of the water. And then the shale was laid on top, then conglomerate and sandstone. It really is that easy. Okay, here comes a cool thing. We've got pieces of granite in the sandstone. Which is older, the granite or the sandstone? This is the law of included fragments. A fragment has to be older than the rock that it's included in. Well, that makes sense. If you make, let's say, a macaroni picture for your mom on a paper plate, and then you take a picture of it, which had to be there first, the picture or the macaroni plate? The macaroni plate had to be there first. Here's the macaroni plate. That was first, then the picture was second. This is the picture. So, granite had to be there. It looks like it got eroded. Then sandstone came along and the granite got included in the sandstone, and then shale, and then limestone. In this case, however, take a look. Sandstone is included in the granite. It looks like the sandstone was there. Granite got intruded into this rock as a molten form, and pieces of sandstone as xenoliths, you'll remember that from a previous chapter, got included. And those probably would have been baked into quartzite. And then shale, shallow sea, and then limestone, also shallow sea. This really is pretty easy. Oh yeah, sure. Let's see what we can do here. We've got granite, we've got limestone again, we've got sandstone, and we've got shale. So what happened first? It looks like these sedimentary layers were laid down first. Then the fault came along, Now, a fault always has to be younger than the rocks across which it cuts. You can't have the fault there and then get the rocks. And then 3, the granite came through. And then 4, this area was worn down. And then 5, the rest of these guys were laid on top. Pretty cool. It really is easy. Alrighty. Now, if you want to really get good at this, pause here and try it yourself. We know that F was probably last. We know that A had to go through these layers, so A has to be younger than these, but older than N. We see that there's some tilting going on. We see that there's a fault. I really am going to leave this one up to you. You can pause it here and give it a shot. You may see this on a test someday. Hint, hint. Okay, remember that really complicated drawing we had earlier? Let's go at it step by step. Here's the seafloor, here's water. Those of you who are really lazy, you might want to stop there. But we're going to go another step. Okay, like we talked about before, there is the thing called the law of original horizontality, which says rocks that are laid down in water tend to be horizontal, and rocks that are on the bottom are the oldest, rocks that are on the top are the youngest. Any face between two rocks is called a contact, and any big group of rocks is called a formation. For example, this is called the Tarberg Formation because these rocks are kind of mixed if you go look at them carefully. This thing is called the Birkeland Formation. And this is Principal Skinner, different from the principle of cross-cutting relationships. It is appropriate because you remember earlier we had the Skinner Formation, which is kind of cool. Okay, which is older here? The sedimentary rocks or the granite? Take a look. The sedimentary rocks got baked by the granite, which means the sedimentary rocks had to be there first. The granite intruded, frying these little rocks. Ah, it's hot. Sorry. Okay, let's do another thing. The sedimentary rocks had to be there. They got tilted. Then the granite came in. And then something got worn off. Then you end up with some sediment being deposited on top of that unconformity, a big period of missing history. And then more stuff laid on top. And then something cutting through it. Remember, this is called a volcanic dike. And then more erosion. This is getting easy. No, it's not. And then more stuff being laid on top of that. And then the Hamlinville Formation, and then the Skinner Gulch limestone on top of that. And if you want more, you can go to ClassZone and do it, or look at a place called Geologic Time. Just look it up on the web. Now, inclusions. As I already told you, if something is included in something else, the first something has to be older than the something else. So in the case of the granite, it has to be younger because it has older things included in it. If you make a cake with raisins in it, which did you have first, the cake or the raisins? You had to have the raisins on hand before you could make the cake. These are the raisins in your cake. Now to be geologic, this is called the law of included fragments. Unconformities, we've referred to this, but let's look at them. Geologists like to get crazy, but if you look, we have a whole bunch of horizontal layers right here. And then right underneath this layer, there's a bunch of tilted stuff. What's going on? These guys were laid down, they were tilted up, they were shaved off, and then these layers were laid on top. This surface right there is a few 100 million years of missing time, which is really kind of cool because you have super old stuff in here, and then it goes to a lot younger stuff in here. This jumps up to what's called Mesozoic rocks. What does an unconformity or a disconformity look like when you're looking at fossil sequences? Well, we know that fossils kind of go in this order. For example, if we find a rock that looks like this, we know we have the top 2 layers, we have the bottom 3 layers, and these layers are missing. That's called a disconformity. Now again, geologists like to go crazy naming things. To me, it's not a big deal. Correlation. What's correlation? It's just matching areas with other areas. It's like puzzle solving. You may remember this from the section on plate tectonics. We find the same fossils in South America and Africa here, in South America and Africa there, in Africa, Madagascar, India, and Antarctica here, and crazily enough, in South America, Africa, Madagascar, India, another little island, I think that's Ceylon or Sri Lanka, Antarctica, and Australia. You think there's a reason all these continents seem to fit together in a puzzle? Probably not just coincidence. They really were together at one time. Now, in northern Arizona, southern Utah, southwest Colorado, all these same rocks continue across there. Sadly, we give them different names. But if you drive from Phoenix up through Bryce, Zion, or into Mesa Verde in southwest Colorado, you're going to see this entire sequence of sedimentary rocks. Or if you drilled down with a well, you would see the same thing. Now, on occasion, certain pieces of this are missing, like we just talked about with the disconformity. But in general, that's the sequence. And here is a detailed sequence. Really old rocks are called the Vishnu schist. Then you have a sandstone, a shale, something called the Mauve Formation, Temple Butte Limestone, Redwall Limestone, Supai Formation, Hermit Shale, Coconino, Toroweap, Kaibab, and then on the very top is the Moenkopi Formation, but you don't find this very often at the Grand Canyon. Usually the top is just the Kaibab Limestone. If you go up into Zion, what you find is the Kaibab is the oldest rock you can find on the surface, and then on top of it is Moenkopi, Chinle, Wingate, Kayenta, Navajo Sandstone, and the Carmel. If you go to Canyonlands, you find this stuff, which they have renamed, this stuff, and then the same sequences. If you go up to Mesa Verde in Colorado, you see the same things, but more recent rocks. And then if you go up Bryce Canyon, even more recent rocks. These are the ages of the dinosaurs. This is the mammal age starting here. Now, when we look at Glossopteris fossils, in Africa, India, Australia, Antarctica, and South America, we find the same sequence of rocks, and we find the fossils in the same order. It's really kind of cool. And then the fossils die out, and you find basaltic flows on top of those. This is getting a little bit detailed, but we won't care about that. Now, key beds, or index fossils. Imagine about 1 million years from now, you went into a time machine and then you came back, don't ask me how, and you found a layer of rock with Sony Walkman in it. What would that tell you about the layer of rock? Those of you who are thinking will know that it had to be formed sometime after the 1970s, 1980s? Not sure when the first Sony Walkman was. But we also know that the Walkman wasn't around for a very long time. So if you find a rock with Sony Walkman buried in it, it was probably formed sometime in the 1970s, 1980s, deposited in a flood, and then preserved. The same thing happens with trilobites. Trilobites, now we say they're short-lived, but short-lived in this case means somewhere around, what are we looking at? 58 to a lot of million years. Let's just put it that way. Trilobites are like chitons. If you go to the ocean, sure, you can find these kinds of things stuck on the rocks, but there are all kinds of various species of trilobites. They were relatively short-lived, they were widespread, and they're recognizable. So if we find a rock with a particular type of trilobite in it, we can date the age of the rock. It's kind of cool. I'll stop here and come back in just a while.